Okay, I'm going to take a look at Chapter 3, Equilibrium of a Particle. So particle is basically defined as, this a small quantity of matter. So in our case, we're basically considered it that we can think about the object as like a point. Okay. All right, so we're going to look at this idea of condition for equilibrium of a particle. Take a look at free body diagrams. And then the second part, we'll look at coplanar force systems and three-dimensional force systems. Okay, condition for equilibrium. And basically the idea is that if you sum, this is a vector, right, of forces. If you sum all the forces in a system, the vectors of those forces, so you have direction and magnitude, if you took them all together, and you would come up with a zero result, right? So everything, essentially all the forces cancel each other out, and you have no acceleration. Okay, so you could have an equilibrium system if you have something that's at a constant velocity. That's also equilibrium. You can think about it in terms of like a car traveling down the road and the forces that are acting on it. There's wind resistance and friction acting against the motion of, the drive of the engine. Okay, those would cancel each other out if you're at a constant velocity, and if you're at a constant elevation, the weight of the car would be canceled out by the normal force pushing back up against it. So that's also an equilibrium condition. Okay. But here's when we're talking about where we could take and think about an object as a particle, or what the impact on a particle, we have one equation for that, and this is the equation. Just the summation of all vector force vectors is equal to 0. All right. Now, one thing this doesn't take into account, which we're going to take a look at later in the next chapter, is this idea of a moment or rotation. Okay. So that condition also has to be held. If we are dealing with a particle, then of course we don't have any, we don't have to worry about the rotation. We're just dealing with a point source. Okay. But when we have real world objects, we also have to consider, almost in all cases, we have to consider the moments. Of course, if we have cables that are all connected like at one point, then when we're analyzing that point, we don't have to worry about moments. Okay. But recognize that, often the second part of the equation would be the summation of moments, which are just rotations, would also have to be 0. So this one only applies if you can take everything and consider it to be like a point or a particle, or acting on a point or particle. Okay. So here's an example. Why do we care about this? Well, let's say we have an example is that you're holding up a crane and you want to make sure you do an analysis of this. You figure out what tension's in this direction and the weight's in this direction. And you want to analyze it to figure out what the forces are, let's say, in these cables, to make sure it can support the weight. Okay. Here's another example. Okay. Now, one of the things here, you're going to see that we could, in this case, we could pretty much represent it two-dimensionally, right? And maybe we care about these cables, make sure this can support the weight, and this cable here can support the weight, and also these. So you'd have to make sure whatever the weakest point can support that weight, all right? And same idea, we want to make sure it doesn't fail. Okay. So how you could do that is like you could say that the particle, or whatever the particle is this point A, let's say, and these forces are acting on that point. Okay. So if we look at point A, what do we have? We have some tension pulling up. We have some TB and TC, so tension's going down here. So in this case, we're taking part of the system. We're just looking at like the ring, what's happening here. Okay. Here's another example. Okay. You have cables connected. And let's say, you know the force pulling in this direction, and you want to determine the tension in these cables, okay, to make sure that they can support that, right? And what's the point of that? Of course, we want to make sure that we have a strong enough cable, or what the size, in terms of the size of the cable, right? And one of the things also is that if you were to design something like that, you'd have to think about a certain level or certain factor of safety. You know, if that's 2 or 3 times what you expect it to pull, or even more than that. Okay. All right. Next thing is a free body diagram. Okay. So free body diagrams basically are just drawing like this system, the forces that are involved in the system. Okay. Okay, so what we'll do is take a look at an example and how you can use a free body diagram for this particular problem. Okay. So in this case, we can be, let's say we're looking for the tension in these cables. All right. So, uh, so like in this case, we're saying if this system is in equilibrium, we assume it is two-dimensional. Okay. We're also going to look at three-dimensional later. Coplanar, meaning essentially that it's living in the same, you know, all the forces are acting in the same plane. And we can use it, we can represent it with, you know, our XY coordinate system for this. Okay. So you have some cables and you have a weight connected and you want to find the tensions in those cables. Okay. So first thing is you need to isolate part when you're building like a free body diagram. You need to isolate part of the system. In this case, we're going to take a look at just this ring A, and we're going to think about the forces that are acting on that ring. Okay. So you can isolate it. So we're just going to isolate this part of our system. We're cutting it out from its environment. And as far as why we can do that is because if you think about it, as far as what A sees, it's going to see some like force trying to pull it up this way, another force trying to pull it out that way, and another force trying to pull it down. Okay. Now what we recognize is that this is in equilibrium, you know, provided it doesn't break, and it's at one point. So we know that all those forces have to sum up to zero. All right. Okay. So here's our free body diagram at A. All right. So we're just looking at it from A's perspective. What we can see here is that, you know, if there's some, these are just cables. So if there's some tension pulling from this point and from A and up, there'll be an equal and opposite one, of course, pulling from here down. It's the same cable. It's going to have the same tensions in it. It's just that from B's perspective, it seems like it's a cable, it's a force pulling it down. Okay. But since it's the same cable, it's the same magnitude of force, right? So we can figure out what the tension is in that cable just by analyzing this one point, right? Same thing over here and the same thing here. So this is enough for us just to analyze the system at A. Okay. Okay. So just if you could define the forces on it, you know, the active forces and reactive forces. So the idea being, you know, of course, in our case, if we thought about it just in terms of like reactive forces, in our case, if we think about that, we'll use this reactions will be something we'll cover a little bit later, and we can think about it in terms of some active forces. So these forces are trying to pull it. Okay. So here's the free body diagram. Okay. And here is just the this part here is just the force acting down. Okay, 392, which would be 9.81 times this thing. Okay. Okay. So continuing on, here's our equilibrium condition. So we have these are our vectors, FB, FC plus FD equals 0. So you could also write it like this, right? So what we have, we're going to have the summation of all the forces in the x direction, the magnitudes, plus the summation of all the forces in the y direction times I times j. But these individually would also have to be 0, right? So when you're saying that the vector is equal, the summation of all the vectors is equal to 0, what you're really saying is that the individual components must also sum to 0, okay? And that's all this is showing. All right. So we could also write this as just the summation of the forces in the x direction, the magnitudes, and the sum is equal to 0, and the summation of the forces in the y direction is equal to 0. Okay. Equations of equilibrium. So this author uses E of E. Okay. So one of the things we recognize here is that we have two equations. We have two independent equations, one here and one here. So we have the ability to find up to two unknowns, okay? Which is good because if you think about it, we know what the tension in this one is going to be. We've already got that defined, F of C. So FD and FB are the ones we need to find, okay? So we write the equations. All right. And we use as before, we use the trig functions to do that. And if we're looking for, here is like the x component of FB. So really it's just the adjacent side over here times this magnitude, which we don't know what it is yet, times the cosine of this angle. Okay. And then of course the other one, which would be the vertical one, is just the sine times the sine of the angle times f of b. Okay. Now what you recognize here is that FD is negative, and really it's because of the direction we drew it in. Okay, so it's going off to the negative x. If I had drawn it in this direction, let's say I didn't know what that direction was, that would be a positive. But what would end up happening is that your end result would be negative, which would just tell you that essentially it's in the other direction. Okay. This problem's not too hard to to figure it out. Like which is it, under compression or tension? That's pretty straightforward. That it's going to be under tension. It's going to be trying to pull it out this way to the left. And the only point of something like this is that, let's say f of d, your answer came up to be ever becomes negative. If an answer for a force ever is negative, all it really means is it's in the opposite direction what you thought it was. Okay. All right. So here's our two equations, and so we have this one has two unknowns, but the second equation only has one unknown, so we can actually go and solve for that. We could solve for f of b. So now we have f of b, and then we can plug it back in here and solve for f of d. Okay. Okay. So that's basic, like a two-dimensional problem with forces, right? We also have some other forces that we'll take a look at. One is springs, okay, and deformation of a spring. So how much force? So the force acting down is just going to be whatever the spring constant is, which is force divided by length. So Newton meters, let's say Newton per meter, times S, which is how much was it deformed. And these are so-called, linear springs, or at least in that linear range of operation. Okay, and this works for both compression and tension. Okay, so the idea is that, let's say the unstretched length is L naught. Okay, the length from here to here, and then all of a sudden you put a force on it, and how much would it deflect? It's depending upon the characteristic of the spring. A number of newtons per meter times S, whatever that deformation is. Okay, and that's basically it for force in a spring. Okay, now we also have pulleys. We're going to look at pulleys, and what you're going to recognize here is one of the things we say about these. When we go and solve them, we say they're frictionless pulleys. So whatever tension is in T1, this is the same cable, so it's going to be the same tension in T2. Okay, that's kind of the main point. Pulleys are used to redirect the forces, but the tension is going to be the same. So anytime you find like a cable wrapped around multiple pulleys, the tension's the same everywhere, essentially in the cable, right? Okay, so T1 is going to equal T2. All right. Okay, and of course it only can support tension, not compression. All right, and here's another one when we're looking at a smooth contact point, okay, on a smooth surface. And the only force that's going to be acting in this one due to the surface is the normal force. All right. Now, if there was friction force, of course, that would act against this also. If it's in if it's in motion, or even not if it's in motion, if there's some tension on it, we would also have to include that friction force, right? So it would make the problem a little bit more complicated. But for now, we're just going to consider them it to be a surface. Just a smooth surface. Okay. So if we went and created the free body diagram of this, we have basically the center point of this, whatever it is, roller or whatever. We're taking it basically at the center of this mass of this cylinder, And we have a force, a normal force, a weight, and a tension. And since it's a smooth surface, this is the total system. Okay, that represents all the forces. All right, and that basically ends, sections 3.1 and 3.2.